Allocators seem to have become all the rage lately, but why? Odin and Zig are probably the two languages most full of allocator discussion, but even languages with automatic memory management like C++ and Rust have mentioned allocators, and Go and Java have arenas and some new APIs, so what's that all about? Well, let me just immediately say that C++'s allocators are weird and pretty different, so I won't be covering them today, but pause if you want the gist. Anyways, for the rest of the languages, what problems do allocators actually solve? And really, what even is an allocator? Well, when you write code, you tend to have data that you work with. Numbers are the most fundamental data, and they're combined to create text and images and 3D models and sound. And all of that needs to be stored in memory. And that memory has to be allocated to your program in order for it to be able to be used. So an allocator is just anything that handles that. Often, allocators will be built on top of other allocators, divvying up memory that another allocator gave them, and at the root of all this is usually going to be the operating system, but if you're working without an OS, you're usually on your own for this sort of thing. Memory pages aren't exactly allocators, and they're such an incredibly deep topic that I can't explain them entirely here without getting into OS design. But basically, a page of memory is one unit of memory handed out by the operating system to your process. Usually, it's 4 kilobytes, but it's possible to have larger ones, or even multiple different sizes at once. These are large contiguous blocks of virtual memory that are individually handed out to your process. Pages aren't generally the sort of thing that you'd use directly, though. You almost always want to build another allocator on top of them. The most common and generic type of allocator that's often built directly on top of pages is the heap allocator. In C, malloc is most people's default allocator, and it's what's called a heap allocator. It's built directly on top of memory pages as a way to individually manage smaller allocations. As the name implies, it's basically functioning as a giant pile of memory. It has no particular order or structure, and it's just a big blob. When you want some memory, you ask the heap allocator for some number of bytes, then you give those bytes back when you're done with them. The thing is, you don't actually need to do this for every single byte. As you know, if you've used basically any language ever, the memory for variables is managed automatically. Now, these variables may be pointers to heap memory that isn't managed automatically, but you never need to individually allocate any variables yourself, and that's because of the stack. A stack allocator is one of the simplest types of allocators, and it's probably one you use every single time you write code. When you declare variables, they go on the stack. Some higher-level languages with automatic closures will move variables onto the heap, but in C, that never happens. Stack allocators work by starting with a big block of memory as well as an offset. New memory is allocated by putting stuff at that offset and advancing it, storing the last offset at the end. And you're only able to free the most recent allocation. This does make it somewhat limiting, since it doesn't work for arbitrary allocations, but a lot of basic allocations do work for it. As it turns out, in a C-like language, every function call works this way, ending before the caller does. When A calls B and B calls C and then D, we can represent all of these using a stack. This is called the function's stack frame, basically just the variables that it uses during its execution. Typically, allocation on the stack is fixed. This means that the compiler knows exactly how many bytes each stack frame needs, but it's not technically required. C is a function to perform dynamic stack allocation, it's just often considered bad practice. So, what are the actual benefits to the stack? Well, there's a few. Firstly, it's lightning fast. Allocating is as simple as one addition in most cases. Additionally, everything is contiguous. This makes it super cache friendly and it wastes almost no space. You do need a tiny bit of bookkeeping though, since you need to store the last offset. So, what if you want to absolutely minimize wasted space, make the allocator even faster, and simplify the management even further? Well, you'd make an arena. Arenas are a bit like a stack. You have a pointer and a big chunk of memory, and you allocate by putting data into that block and advancing the pointer. The main difference is that arenas don't require storing any data per allocation, since they actually don't support freeing allocations whatsoever. That may sound like it's not very useful, but it's actually super good for a ton of stuff, because the key insight is that you can instead free the entire thing at once, so you never have to store pointers to your individual allocations. Consider a case where you're setting up the UI for your game. Ideally, this stuff should be super basic. It shouldn't need much special handling, and it should be very fast, since it's just simple UI layout. The issue is that you need to display info to the player, like their health, money, level, and stats. All of these need to be strings in order to be drawn to the screen, but they're stored as numbers, and turning a number into a string requires an allocation. We can't use the stack allocator here, since we need these strings to be valid all the way until the UI is rendered, which is usually long after the layout, at the end of the frame. We could heap allocate, since that allows us to free at any time, but where would we actually store these strings in order to free them? They would need to be freed at some point, before the next time we do layout, since otherwise we'd be leaking memory. They could go in some list of things to free later, but that itself has to be allocated and stored somewhere, and it's slower and easy to forget. This is one of the best use cases for an arena. Let's have an arena that we use for all of our per frame UI data, so that we can turn our numbers into strings and guarantee that they live until the UI is rendered. Then we clear the arena at the end of every frame so we're ready to do it again next time we draw the UI. Arenas have all the same benefits as stacks, with the additional benefit of not requiring you to care about the lifetimes of any individual allocation. So, now that you understand a few basic types of allocators, how do languages use them? Well, languages like Zig, Odin, and C3 feature them as plain old in-language types. They're nothing special, but they are part of the standard library, so the whole language supports using them, which is super useful. The exact implementations differ a lot, but generally it's always some sort of interface. Rust's is a bit more complex. It is an interface still, but because Rust doesn't typically allow you to just allocate whenever, allocators are specifically a part of collections, like vectors, boxes, maps, and strings, and these collections are generic over their allocator implementations. What's the point of a language with automatic memory management having allocators? Well, just because the allocations are automatic doesn't mean they don't happen. While Rust's automatic memory management is certainly more efficient than a full garbage collector, it still often results in heap allocation, and since Rust wants to give users as much control as possible, opt-in explicit allocators are a nice solution to the problem. Here's where Java and Go come into the picture. They're garbage collected languages, which means they're explicitly trading some amount of speed for generic simplicity with automatic memory management. I should also mention that Go's arenas are very experimental and have been in a sort of weird limbo for nearly 4 years, so take all this with a grain of salt. The idea, though, is pretty simple. Arenas are a super fast, super basic way to allocate memory, so exposing an API is the best way by far to give the programmer some access to low-level memory controls when they need it. Go's arena API is a full-fledged arena, letting you allocate types and slices and all of that, but Java's isn't quite the same. Java's arenas are mostly intended for their FFI stuff, so you can't actually allocate your own object there. Instead, you're meant to use it for allocating raw memory layouts and passing pointers into C functions or giving C functions pointers into the arena. You can also use it for mapping files into memory. The heap, the stack, and arenas should cover almost all of your allocation needs, but I'll close out the video by covering a few more. Like I mentioned at the start, it's common for one allocator to sit on top of another, and that's the purpose of this allocator. Odin calls it the tracking allocator, as does C3, and Zig calls it the debug allocator. I'll refer to Odin's implementation here. The idea is that it sits on top of another allocator, and it intercepts every allocation request. When you allocate something, the tracking allocator notes it down and stores it inside of a hash map, including info about how big the allocation was, and the specific code location that did the allocation, before passing it along to the allocator that it was wrapping. When you free, it first ensures that this address was properly allocated and panics if it wasn't. Otherwise, it removes it from the map and uses the underlying allocator to free the memory. When you're done with your program, you can loop over the entries of this map and print everything that you forgot to free, and see exactly which line allocated what. Another interesting allocator is the buddy allocator. It relies on taking a large block of memory and splitting it recursively to fit allocations. This makes it similar to an arena, being pretty cheap and using a fixed block, but it's actually possible to free individual allocations with the buddy allocator. The downside is that it's pretty complicated, and it wastes some amount of space, since allocations are always rendered up to the nearest power of 2. Still, it's common inside operating systems and other places where a heap allocator isn't something to take for granted. One last honorable mention is garbage collectors. They are technically an allocator, and it's possible to make them work with a standard allocator interface, but usually a garbage collector will be implemented as a language feature. Still, it's code that handles giving and taking memory to and from your program, so it does count as an allocator. So, if this video helped you, feel free to leave a like, and subscribe if you want to see more. I'm trying to make helpful videos every single week teaching low-level programming and programming language design. I'm also releasing daily YouTube shorts explaining every single one of Odin's features, so if that interests you, feel free to check it out. Anyways, that's all for right now, and I'll see you next week.